All right, so my presentation today is about a, about a scalable game server in Python. Specifically, it's not meant to be for any game specifically. It's more a investigation on proper use case for it and where you can apply it and make it fit almost anywhere that you need it to. A little about me is I'm a DevOps engineer at Clever. I do a lot of cloud work there. As a hobby, I do Android ROM and kernel development. So, whereas apps are what you normally use and download from Play Store, mine would be the actual system as a whole. Big Python enthusiast. I love using it for anywhere from little quick one-off jobs to full-on applications. It fits really easily, and the bar for entry is really low. So, I also have a lot of hardware experience, or not experience, but I like playing around with hardware. And this is my first talk here, so. So I was told a couple of months ago that I need to make a backend for a game server, or for a game. So I kind of freaked out at first, like, oh God, what is a game server? Like, that's a lot of data coming in and out. But then I realized it's really not. The game isn't anything special. It's just a fancier UI, maybe a little more fast-paced. And I kind of broke it down into smaller chunks that I was able to more digest and figure out the whole plan of action. So the picture shown there is kind of the way we have it set up. Of course, you can add or drop in anything else you need to in that pipeline. But some of the big aspects of it were the communication. How are we going to talk back and forth? Are we going to use a JSON API? What are we going to do for that? Security. If you're making a big game, you don't want people being able to just go in and cheat with it. Managing state. So a big thing about scalability is that you've got a lot of work put into making your state grow or be able to be accessed while your application grows. That fits real well with scaling as well. And reusability. You don't want to put a lot of effort into one project and then never use it again. You kind of want to have something that you can take theory from, if not code. So for this example, the idea I have is an MMORPG. Things you'd need to transfer back and forth are world location, if you've used an item, your health, mana, buffs, anything like that. So there's this, I don't know if it's software, but Google has it. It's called PROTOBUF. It stands for Protocol Buffers, and it's a binary data serialization library. It can compile down into C, C#, Dart, Go, Java, many other, as well as Python. The format for it is very simple, so you can actually have a message structure like I have right there, and you define basically a data type and the name of that value. So, for example, a person have a name that's a string, an ID that can be any integer of 32 bits, and then an email is optional. The numbers next to it just denote, hey, these are the order that we were expecting them in. It's very simple to use. It gives you a definable properties that you can look back to instead of having code that you would have to read the code again to figure out the structure of this packet. So it makes updating the actual message structure that you send back and forth quite simple. It's very simple to use. To compile it, you actually just use proto-C, and you can do -- language out, and that will tell it, hey, output this language binding and put it in this directory, and then star.proto is just any proto files. For example, like we have here, we have a packet. This is a stripped out version of one that we actually use. It's kind of got a lot of the theory behind it. So you have your packet type. So you can define several different packet types. This one's a generic packet, whereas a packet type would be kind of a message. So you can have an authentication one for game data like world location, regular data like consumables used, points scored, and a heartbeat, which we'll get into a little bit more later. And so in that structure, you have those possible packet types, the sequence, so you'll want to send them in order. That way the server knows, hey, this one came first, this one came before that. Message link just helps for deserialization. The message is a little bit interesting, so we use a different way of doing that when it's auth. But for this case, we're defining a packet that you can send through a network. And in that case, the message will actually be the message, so like game data, world location, stuff like that. Then you have timestamp, which is self-explanatory. And then the CRC 32 checksum. So that one's pretty interesting because it's a very fast redundancy check to make sure that the data you're sending is not corrupted. And then a player ID. You kind of want to tie a player ID to each message you send back and forth. Kind of went over that in the same way. I will say that message and packet type go hand in hand. So if you have game data coming back, you want to say, hey, this packet type is game. And using it is very simple. You import the compiled PROTOBUF library, and you create a new packet in this case. You can just set its properties like you would any old object. It's quite simple. And then at the end, you just tell it to serialize the string. That's the Python example. The conventions actually change depending on what language you go out. So if it's like C#, it'll use C# conventions for variable naming, where it's like a capital letter for the properties. So it's pretty interesting that way. And another part of the communication is TCP or UDP. So TCP is Transmission Control Protocol. It's what most by default browsers use. It's a call and response. So if you send a TCP packet, you send it out, and you might not get a response on the other end, but TCP makes sure that it got there. It verifies that and does error correcting and stuff like that. It's got a lot of really neat features. It's the same way that if you download a file, that even if the packet doesn't get there, you'll still get the right data. It'll resend it as much as it needs to. UDP, on the other hand, is very fast. It doesn't care if it receives it. It's a broadcast. It has a lot of higher priority in a lot of routers because it can get corrupted, it can drop, and they want to make sure it doesn't. And a lot of game servers end up using UDP. It doesn't care if it gets there. It doesn't care if it's been corrupted or not. So you do have to handle that on the servers, say, hey, if the CRC checksum, for example, doesn't match, you probably don't want to look at this data. It's been corrupted. A lot of games use UDP because of the speed is key. And I know you'll notice at some point UDP packet dropping if you played an online game and you move around a little bit and all of a sudden you seem to jump for a millisecond where you were. And that is a UDP packet dropping where the next packet that it sent is like, okay, yeah, we're both in sync now. We know where you're at in the world location. Coming over that. And then, so that's how we do communication. We're using UDP and we have a definable packet structure. And so how do we stop hackers? We don't want to let anyone to create a packet and lie about what their state is. And we don't want to trust the client input. We don't want them saying, oh yeah, no, I've got infinite health, it's fine. And we have this method that's an RSA and AES handshake. So RSA is public key encryption. You have a private key that the server holds that can decrypt and encrypt any data, and the public key can only encrypt the data. So HTTPS uses this, where you get the public key, you sign anything that you want to send to the server, and only the server with that private key can read it. AES is two-side encryption, so anyone with the key can unlock it, like a padlock. A handshake was sent through an authentication packet. And basically in that packet, you just say, hey, I want to authenticate, and here's my AES key. But you just don't want to send your AES key through plain text. Anybody could sniff it and be able to work efficiently with it. AES is actually a federal government standard as of 2002. And so what we do is generate an AES key for that session. It's basically a random 256-bit integer. There's also a couple other key sizes, but that's kind of the standard and the highest that you can use. It's not just random. You want to make sure that it's actually good random data, not pseudo-random. Any crypto library will be able to do that for you. You get the public key from the server that it can either generate or you can precede it, and you sign your AES key with the RSA key. That way, when it's sent there, only the server can read your RSA key or AES key in plain text. The server decrypts it and puts it somewhere that can remember it. Usually in memory, you don't want to write it to disk. We use Redis in this case for this because it's got in-memory key value store. So we tie the player ID to the AES key. So anywhere in that transaction cycle where it needs to get the AES key, it can pull it by player ID. And that's also why we tie the player ID onto the packet. All packets use this message. So we have the packet structure. The message property on that is another PROTOBUF file that you can define, and you encrypt, or you serialize it to a string and you use AES to encrypt it. That way anybody can see the data, they can see the player ID, they can see the checksum, but they can't see the actual contents of the message. This is actually what Valve uses in the Steam Link. I ended up doing a little bit of research on that and seeing that they use the same way, same handshake with RSA and AES. And as far as not trusting the user, you want to do all your health and damage calculations on the server. Don't let them tell you what their health is, you tell them. Just like your boss gives you a paycheck, you just don't take it out of their account every month. And any database will work. The higher availability, the better for scalability. You can shard it, you can run different clones of it, whatever works, run a cluster. So that was a lot of theory, and I know a lot of people might be thinking, well, where's the Python part of this? So we did implement this on Python, about 161 lines of it for the UDP server. We didn't do workers in UDP, but workers can be any language that can read from a socket. Apparently I did not talk about that in here. I'll show you a code example in a moment. But basically, that's putting everything together. It's listed on UDP port. For every packet that comes in, you want to spin off a new thread to throw it where it needs to fast. You don't want your server to be waiting for another, or be stuck in a period that is cycling when a packet's coming in. You don't want to fill up your buffer. So you want to take it and throw it away as fast as possible, just so you can keep high availability. And then a worker will pick it up from Redis, for example, or any message queue for that matter, and will do the heavy lifting on it. It will do the database transactions. It will calculate what the new value should be and put it back in Redis, and you have another thread on UDP server that replies to the socket with just the PROTOBUF. So all the UDP server does, takes it, throws it into Redis, a worker picks it up, does it, and it listens for responses and just throws them back out to the client. This allows the UDP server to scale up as high as it's like because it does not hold state, it doesn't matter, and allows the workers to scale up as long as the database and Redis are able to stay in sync. So for a real code example, go here. I have this on GitHub. Anybody can go to and view it. It is a proof of concept of this. This might look scary, but it's PyCrypto, and it's a certain lot. Oh, yeah. 1 second. Sorry. Display. There we go. We should be able to see both sides now. Let me zoom in here. Okay, so basically what we have here, we talked about the PACKETPROTO here, and that's basically the same as in the presentation. You've got your packet types and the data. And then I did not go over this in the presentation. So you have server and client communication. So a client, or in this case, a server tells you where you're at in the world or how many coins, health, or mana you have. And then the client will tell you, hey, here's where I changed X, Y, and Z, and here's where I've lost health or used coins or used mana. And things like this, you want to be smart about your data types, that you don't want to be able to lose negative health. it's not perfect implementation. This isn't a full game. This is a proof of concept, so you can always change them as needed. I added a Docker Compose in here because I like using that for services like Redis. So I basically just threw Redis in there for you. And then the interesting stuff is in the workers, UDP utilities, and the client. So there's nothing truly special in here. Let's look at the UDP utilities first. It's basically creating a packet. You give it a packet type like game or data, a message, and a player ID. And it will make it add a sequence number to it, and then set the message, add the timestamp, serialize the string at that point, and make the CRC checksum, and then set it, and then return it out. That's just a helper function to add timestamps and CRC and stuff like that on the fly. And an AES tool is a little class that I made that is basically a couple of interesting ways, or just using the PyCrypto library to do AES operations like encrypting, decrypting, padding the messages because they have to be in 16-bit blocks. And it's just a simple way to encrypt, decrypt, and create a key using standard methods. Look at the server here. This one's a very stripped down version of the one that we use with a lot of our stuff taken out, but still proof of concept to show the theory. Basically, when you start it out, you take an RSA key, read it, and store that in memory and be able to give that to the client. You bind to a UDP socket. You can define your own port. In this case, I believe this is using 1234 for this example. And this interesting bit of code is to go ahead and declare the channels that you're going to use in Redis, so that you can use the publish and subscribe methodology to read and send packets back and forth to your workers. And basically all this is just looping and listening for packets and sending them out. So when you get a packet, it gets put into handle packet, and this is run on its own thread. It creates the packet and checks what kind of packet it is. If it's a heartbeat, we know that we want to send it back to the server and say, hey, we got your heartbeat, we're still alive, everything's working okay. We do a little CRC check here to make sure that we're good. That's to send back a heartbeat. Ping pong is what we use in this example. Authentication, so we'll take the RSA key from earlier and decrypt that message so you can have the AES key, and it will set it in Redis here. That way you're able to refer to it at any time, and it sends a heartbeat back to say, yes, we're alive now. And then in this case, if it's any other packet type like game or data, it will forward the packet to Redis. And so all that does is it pushes to a list, and it will publish just a blank message to that. So you can say, hey, you want to listen on there. This one is what listens to the packet replies that the worker has made. And all it does is gets the message. If it's an actual valid message, it'll parse it and just send it straight out to the server, fast. From there, the worker is here. This one's very simple. It doesn't actually do anything. There's no database connected to it. It will make a dummy server reply and send it back. So in this case, it's not really efficient. I threw this together in a couple of minutes, but it works the same way as reading the packets for replies. It will subscribe to start here. You'll connect to Redis, and you will set up a subscriber and publisher. And for each packet that you're expecting, you want to make a new thread to work on it. And you can do this in any language that you need to, and you can spawn as many workers as you want. In this case, basically pull it, check if it's valid, and then pop it off the list, parse it, and get the AES key from Redis. And for each channel, if it's a game or data message, pull it, parse it, or I missed the ASCII part. So if the channel's getting messages, you'll want to create a game message, so it'll parse from it and decrypt that message that you got. It'll print it out and it will make a reply packet. And the data does that same way, just its own special data that goes in. And at the very end, it sets the address and port from the original packet and publishes it to the packet reply queue so the server can just continually send it back out. And that's kind of how that works. Are there any questions? Yeah.
How do you, like, if you're going to go ahead and change your PROTOBUF, does PROTOBUF handle versioning that? So you can send, like, say, version 1 PROTOBUF to a version 2 server and not throw exceptions on that end?
That's a good question. I don't believe that PROTOBUF has any built-in handling for that. I believe it leaves that up to the discretion of the developer. A lot of times you can actually add on extra properties to the end and it will still work just fine. Implementation on that is kind of up to the developer. I don't think they have anything in place for that.
I have a question about your randomization reporting crypto module.
Mm-hmm.
What are your comments on that compared to the secrets module?
So you asked about randomization in the crypto module versus secrets module. I am actually not sure on that one. For this proof of concept, I just pulled a random, it was a urandom, 32 bytes out of urandom. Not the most secure thing. Ideally, you would want to use whatever is better for that. I'm not sure exactly which implementation is more secure on that. All right, and you had a question?
Yeah, what did you do? Did you load test that at all?
Yes, we did do some load testing with it. It was quite a while ago. The UDP server was able to take a good brunt. I believe we had, I think we got over 1,000 concurrent hits on it. We spun up 1,000 workers and each one of them would send 10 packets of data and game data to the server. And it would see when it crashed or if it did, how many packets were dropped. And I believe we ended up getting it down to about 1,500 active workers and about a 0.1% packet drop on that. Yes.
Can you talk about some of the strategies that you have to use to handle that packet's going to be dropped?
So yeah, what the question was if I could talk about some of the strategies we use for packet dropping and how to handle that. Packet dropping inevitably will happen, and sometimes TCP would be the better choice for it because if, say, you use an item one time, it's not, how are you going to tell the server you used it if that data wasn't fully transported and got there? Because the server needs to count the effects of that item that you used. So what we had to do is basically we ended up almost emulating TCP in that way where I believe we added another property to the packet that said reply to. And in a lot of these cases, a lot of these transactions are one-to-one. So you send a data packet and you'll get a server data packet back. So you say, hey, I changed my X position 2. You'll get back, okay, your new X position in the whole world is 52. The way we did that is that we would check to see, hey, for every packet that we sent, did we get one back? And if need be, we would cycle through and send packets back again as needed. If they did not hit the server, we did not get any kind of confirmation back. There might be some better implementations of that. With TCP and UDP, you get your pros and cons both ways. All right, well, if there's no other questions, thank you for letting me talk, and yeah. Oh.